In the last lecture, we had looked at some general considerations regarding correlations for heat and mass transfer. The transport properties depend on the ratio of convection and diffusion, and that ratio is governed by what is called the Peclet number. Peclet number is the product of the characteristic velocity, characteristic length, and the diffusion coefficient. Okay. And so correlations are written for the dimensionless flux, that is, the dimensionless flux is the Nusselt number or the Sherwood number as a function of the Reynolds number, which determines the flow characteristics, and the Peclet number, which is basically the ratio of convection and diffusion. Alternatively, you could also express these as ratio of different kinds of diffusivities. Okay. So, for example, if you were to express the heat transfer correlation in terms of the Reynolds number and the second number, which is the dimensionless ratio of the momentum diffusivity and the thermal diffusivity, that number would be the Prandtl number. Okay. Is equal to nu by alpha, which is equal to Cp mu by k. Okay. And for mass transfer, that number would be the Schmidt number, that is nu by d, which is mu by rho d, where nu is the kinematic viscosity or momentum diffusivity, d is the mass diffusivity, and alpha is the thermal diffusivity. So, because the transport process depends upon diffusion and it depends upon convection, the convective transport process will depend upon the fluid flow details, okay, the details of the fluid flow, and that is a function of the momentum diffusivity as well as convection of momentum. And therefore, for heat transfer problems, you will have this Prandtl number, which is the ratio of momentum momentum and thermal diffusivity, or it can be written either in terms of the Reynolds number and Peclet number, or in terms of the Reynolds number and Prandtl number. Traditionally, it is written in terms of the Reynolds number and Prandtl number for heat transfer, Reynolds number and Schmidt number for mass transfer. However, that I will show you a little later. It is more compact to write this in terms of the Reynolds number and the relevant Peclet numbers, okay, for these two transport processes. We had discussed the equivalence of heat and mass transfer. Okay. If you have a correlation for heat transfer, Nusselt number is a function of Reynolds number and Peclet number, you can get the equivalent correlation for mass transfer by just substituting the Sherwood number for the Nusselt number and the thermal Peclet number for the mass Peclet number. Okay. And that is because at the microscopic scale, the diffusion processes are identical. Okay. At the microscopic scale, so the first thing is that at the microscopic scale, the diffusion processes are identical. There is an exact analogy between Fourier's law for heat conduction and Fick's law for mass diffusion. If you substitute the heat flux for the mass flux, thermal diffusivity for the mass diffusivity. Okay. That is, as far as diffusion is concerned, there is an exact equivalence. The flow details are exactly the same if the Reynolds number is the same, because the Reynolds number is the only dimensionless parameter that characterizes the flow. So, if the flow details are the same, the convection is the same, and the diffusive processes are exactly equivalent to each other, and therefore, the correlations for heat transfer and the correlations for mass transfer have the exact same form if you interchange the Sherwood and the Nusselt numbers and the thermal and mass Peclet numbers. We had looked at some stronger forms of the correlation, that is the Chiltern-Colburn analogy, where there is this J factor that is defined. Okay. There is this J factor that is defined. Okay. And the analogy states that J heat and J mass are exactly the same and they are only functions of Reynolds number. Okay. They do not depend upon the Peclet numbers or the Prandtl and Schmidt numbers, these J factors. Note that the J factors already have in them the Prandtl and the Schmidt numbers. So, okay, so this ratio of Sherwood and Prandtl power 1/3 or Sherwood and Schmidt power 1/3 is exactly the same for both those cases. This, as I said, holds only for high Peclet numbers and if there is a no slip condition at the interface, that is if it is a rigid interface. Okay. There is conventionally another analogy called the Reynolds analogy, which states that the mass and heat transfer J factors is equal to friction factor by 2. Okay. And this is even more limited. Okay. Gases with Prandtl number order 1 and flows past slender bodies are the only ones that satisfy this analogy. Okay. So, this is very limited. You cannot have an analogy between momentum transfer and mass and heat transfer for two reasons. One is that momentum is a vector. Okay. So, the conservation equations, strictly speaking, have to be written as vector equations for the three components of the momentum, whereas mass and heat are scalars. Okay. They do not have any direction. Okay. Therefore, the fluxes of mass and heat are vectors along the direction of transport, whereas flux of momentum is what we will call a tensor. Okay. So, that we will come back to later. The other reason is because in the case of mass and heat transfer, the quantity that is being transported is different from the mechanism of transport. Mechanism of convective transport is the velocity, whereas the quantities being transported are heat and mass. So, they are different, and therefore, the conservation equations for mass and heat transfer, as we will see later, are linear equations in the temperature and the concentration. Where momentum transfer is concerned, the quantity that is being transported, the momentum, is the same as the mechanism of transport. Okay. And because the quantity that is being transported and the mechanism of transport is the same, there is a fundamental difference. So, that the mechanism itself affects the transport rate. Okay. And it affects the fluid velocity profile, determines the convective velocity, and that convective velocity convects the momentum itself. Okay. So, because of that, you cannot have an analogy with momentum transfer, because they are two different mechanisms. Okay. In the case of mass and heat transfer, whereas the quantity being transported and the mechanism of transport is the same in the case of momentum transfer. So, therefore, one cannot make an analogy between mass and heat transfer and momentum transfer, but however, mass and heat transport both involve scalar quantities, and therefore, the correlations turn out to be the same. We looked at the factors that affect transport. Okay. One is the correlations do depend upon the flow regime, whether the flow is laminar or the flow is turbulent. Okay. As I said, in the flow through conduits, pipes for example, you have laminar flow up to a Reynolds number of 2100 or so, and there is a virtually discontinuous transition from a laminar to a turbulent flow. Okay. Whereas, in the case of the flow past a sphere, for example, the transition takes place through a series of different flow patterns. Okay. So, the pattern of flow will affect the correlation for the transport. Okay. So, it makes a difference whether the flow is laminar or turbulent. Okay. And the flow pattern that is transporting the mass or heat. And the other thing that matters is the surface conditions. Okay. You can have a solid liquid surface where there is no slip condition at the surface. That is, the velocity is 0 at the surface. Okay. That is called a no slip condition. That happens at solid surfaces. It also happens at for example, a falling film on a solid wall, for example. There, the velocity of the interface, the fluid at the interface is equal to the velocity of the solid. which means that relative to the solid the fluid velocity is 0. Okay. So, there is no fluid flow relative to the solid either in the tangential or normal direction, okay, either perpendicular to the surface or parallel to the surface. The velocity parallel to the surface also has to decrease to 0. The relative velocity between the fluid and the solid parallel to the surface has also got to decrease to 0. The perpendicular velocity is of course 0 because the surface itself is impenetrable, okay, that is the definition of the surface. So, therefore, the perpendicular velocity is necessarily 0 at any interface. At a solid surface, the velocity parallel to the surface is also equal to 0, okay, which means that the strength of convection is decreasing to 0 at the surface. Okay. So, that is one set of boundary conditions at the surface. The other is at a liquid gas interface, for example. You can have a non-zero velocity in the fluid, in the liquid at a liquid gas interface. You take the case of a gas bubble, for example, that is shown over here. Okay. You take the case of a gas bubble. The velocity that has to be applied at the interface is the continuity of velocity on both sides and the continuity of stress. If you had a solid, there cannot be relative deformation of the solid and therefore, the velocity has to be 0. Whereas, in a gas you can have a circulation within the gas. Okay. So, the velocity at the surface does not have to decrease to 0. It can be finite in the direction parallel to the interface. Of course, if the bubble is impenetrable, then the velocity has to be 0 in the direction perpendicular to the interface. Okay. But in the direction parallel to the interface it can be non-zero. So, the difference between the slip conditions and the no slip conditions at the interface also affect the transport rates in this case. Okay. So, these are the different factors determining the nature of the correlations. Okay. And the third factor is of course the parameter regime, okay. That is the ratio of convection and diffusion, the Peclet number. Okay. Okay, which is characteristic velocity, characteristic length by the diffusivity. Mass diffusivity for mass transfer, thermal diffusivity for heat transfer, momentum diffusivity for momentum transfer. If this is much smaller than 1, okay, then convective effects are small compared to diffusive effects. Okay. That means that you can neglect diffusion altogether. Okay. And I am sorry, if convective effects are much smaller than diffusive effects, you can neglect convection altogether. Okay. The fluid flow is not contributing to the transport of mass or heat, okay, or momentum we already considered earlier. There we saw that the friction factor and the drag coefficient have to decrease as 1 over Re. In that case we had defined the friction factor and drag coefficient by scaling it by the inertial scales. Okay. So, when scaled by the inertial scales, this scales as 1 over Re. In this case, for mass and heat transfer, when there is no convection, diffusion is dominant, okay, which means that the fluid velocity cannot be a parameter in the equation. Okay. If the fluid velocity is not a parameter, then the Peclet number is not a relevant dimensionless group because it contains the fluid velocity. The Reynolds number is also not a relevant dimensionless group because it contains the fluid velocity, and this tells you that in this case the Nusselt number has to be equal to a constant. The Sherwood number or the Nusselt number has to be equal to a constant. Okay. In the case of flow path particles, of course, there is diffusion from the particle, and the Nusselt number or Sherwood number can depend upon the shape of the particle. Okay. If you had a particle of spherical shape of diameter d, okay, we will see later in this course that in the limit of Low Peclet number, the Sherwood number or the Nusselt number has to be equal to 2. Okay. This is basically the average flux divided by d delta c by the diameter. Okay. For a spherical particle, the diameter is the relevant length scale. This is for a sphere. Okay. You could have similar results for other kinds of particles, other shapes of particles and so on. Okay. So, for the flow around a particle in the limit of low Peclet number, the Nusselt number or the Sherwood number has to be just a constant. Okay. And this can be used to straightaway determine what is, for example, the rate of transport, okay, in the limit of low Peclet number in the diffusion dominated regime. Okay. So, let us look at an example. Okay. A wet particle of diameter d saturated with water dries in quiescent dry air. Okay, so, you have a wet particle of diameter d that is drying in air. Air has no moisture. Okay. It takes 10 seconds for the particle for of the moisture to evaporate. How long will of diameter 10 d to evaporate to 95%. Okay, so, that is the question. Okay. A wet particle of diameter d dries in to the extent of 95% in 10 seconds. How long will it take for a particle of diameter 10 d under the same conditions to dry to 95%? Okay. Now, in this case, the rate limiting step is the diffusion of water in air. Okay. The time required for drying is the depends upon the driving force, that is the concentration difference between the saturation vapor pressure at the surface and the dry air far away. Okay. So, therefore, the time of drying depends on the moisture diffusion coefficient. Okay. D, okay, diameter d and extent of drying. Okay. In this case, the extent of drying is a dimensionless parameter, 95%. Okay, 95% has to dry. Okay. So, the extent of drying is a dimensionless parameter. The difference in concentration between the surface and the bulk of the quiescent air is the same in both cases. Okay, it is the same in both cases. The only thing you are changing is the diameter of the particle. Okay, and you are asked to find out what is the time required for drying. Okay. So, therefore, the dimensional parameters are the diffusion coefficient, right, the diameter d and the time of drying. Okay. And since the diffusion coefficient has dimensions of length square per time, there is only one dimensionless group that you can make. Okay. Dimensionless group, the scaled time of drying that is going to be equal to T d by diameter square. Okay. The scale time of drying, this is a dimensionless group. Okay. It is going to be some function of the moisture difference, okay, or the driving force, that is the concentration difference, okay, and it is going to be some function of the extent of drying. Okay. In this particular case, the conditions are exactly the same between the interface and the bulk. Okay. The extent of drying is exactly the same. Therefore, T d by d square has to be exactly the same just from dimensional analysis when drying is due to diffusion alone. Okay. So, therefore, this implies that the time of drying is proportional to d square, okay, divided by d, okay, times some constant which will depend upon the extent of drying and so on. But those are kept exactly the same between the small particle and the large particle, the particle of diameter d and the particle of diameter 10 d. Okay. So, therefore, if the time taken for drying is t is equal to 10 second for diameter d, okay, if I change the diameter to 10 d, it has to go as d square. Okay. So, it is 10 seconds, the ratio of diameters is 10, ratio of diameter square is 100. So, this has to be 100 times less large. Okay. So, this parameter d square by the diffusion coefficient or length square by the diffusion coefficient is a characteristic time of drying. Okay, it is a characteristic time of drying or a characteristic time for mass transfer for diffusion. Similarly, if it was thermal diffusion, it would be d square by alpha. Okay. So, this is the time it takes for the diffusion to take place in the system, okay, of characteristic length d. Okay. This is called the diffusion time scale. Okay. So, this low Peclet number limit is of importance in flow around particles if the velocity is very small. It is not that relevant for flow in conduits. Okay. So, the reason is as follows: if you have a flow in a pipe, for example, and say you are applying, so the pipe diameter is d and you are applying a temperature difference, okay, delta T, which is the T wall minus T fluid. Okay. How long does it take for the momentum to diffuse across the entire length of the tube, okay, or the entire cross section of the tube? Okay. Time for diffusion across cross section. Okay, this has to go as alpha, I am sorry, okay, I used d here. So, I will use the diameter d square by alpha, where alpha is the thermal diffusion coefficient. Okay. That is the time taken for, if you apply a large a higher temperature at the wall, how long does it take for that heat to diffuse in and equalize the temperature across the cross section? That is d square by alpha. Okay. How much has the fluid moved? Okay. Fluid displacement in diffusion time. The fluid displacement within that time is equal to the time times the velocity. In this case, the velocity is the average velocity. In this case, the velocity is the average velocity. Okay. Therefore, within the time it takes for the temperature to equalize across the entire cross section, the fluid has moved a distance V average d square by alpha. Okay. So, the fluid displacement divided by the diameter is going to be equal to V average d by alpha, which is the Peclet number. Okay. So, this fluid displacement divided by alpha is the Peclet number, and this Peclet number is small. Okay. We are considering the regime where this Peclet number is small. That means that the fluid has moved only a fraction of the pipe diameter before the temperature is equalized across the entire cross section. Okay. Once the temperature is equalized across the entire cross section, no further conduction takes place, okay, because the temperature is now uniform. Okay. All the heat has been diffused across the entire cross section, and once it has convected across the entire cross section, there is no advantage to having a long length of pipe. Okay, because if you have a long length of pipe, you have to pump the fluid through, but you do not get any advantage, any benefit, because the temperature is already equal across the entire cross section and no further heat transfer can take place. Okay. So, therefore, this regime is not of relevance for flow through conduits, the low Peclet number regime. Okay. It is only relevant for heat transfer from a particle, for example, suspended particles and so on. Okay. The transport in pipes and channels is almost always operated in the limit of high Peclet number. Okay. And the reason for that is that in the low Peclet number limit, since convection is not important, the diffusion is dominant, the temperature equalizes across the entire cross section before the fluid has moved very far. Okay. So, that is for low Peclet number. Okay. The Nusselt number or the Sherwood number is just a constant. Next, I will consider what is called high okay. So, that means that V average d by alpha is very much greater than 1, V average d by nu is much smaller than 1. High Peclet number, low Reynolds number. Okay. So, a necessary condition for this, okay, or V average d by nu is much greater than 1, and okay, sorry, not nu, by d for mass transfer, V average d by d is much greater than 1, or for energy transfer, V average d by alpha is much larger than 1, and the Reynolds number is very small. Okay. This can happen only if nu by d, okay, is large, or nu by alpha is large. Okay. The momentum diffusion coefficient is much larger than the mass diffusion coefficient or the thermal diffusion coefficient. Only in that case will you have this particular regime. Okay. This does not happen in gases, okay, because the momentum and thermal diffusivities are roughly the same magnitude, as we will see later in this course. This happens only in liquids, okay, because momentum diffusivities are usually much larger than mass diffusivities in liquids. And in some cases, such as organic liquids, the momentum diffusivity could be much larger than the thermal diffusivity as well. Okay. So, in this case, of course, the transport rate does depend upon the Reynolds number, okay, because the flow pattern is the transport rate does depend upon the velocity, okay, because the Peclet number is large. So, the transport rate does in fact depend upon the velocity. The Reynolds number is low, that means that the flow is laminar. Okay. The Reynolds number is low, the flow is laminar. For a laminar flow, as I had explained in the last class, okay, for a laminar flow, the velocity is a linear function of the driving force. Okay. As I said last time, for the laminar flow in a pipe, for example, the velocity profile is a parabolic profile. The maximum velocity will increase as the pressure gradient increases for a laminar flow, but the profile continues to be parabolic. That is, if I divide the velocity by its maximum value, it will turn out to be an identical profile. Okay. So, for one particular Reynolds number, if I have a parabolic profile, I increase the Reynolds number, the maximum velocity will increase. Okay. However, if I divide the velocity by its maximum value, then I will get the same universal parabolic profile for both of these cases. Okay. If I divide by the maximum value, I will get exactly the same for both of these cases. Okay. That means that the velocity profile is a linear function of the driving force. It is a linear function of the pressure gradient. If you change the pressure gradient or the pressure difference, the velocity at each point changes by that same fraction, okay, or by that same multiple. Okay. This is true for a laminar flow. Okay. It is also true for the flow around a particle, for example, when the Reynolds number is small. Okay. At each point on the particle, okay, or at each point in the velocity profile, if I change the free stream velocity, okay, the velocity direction is the same at each point, only the velocity magnitude increases by a constant factor, the exact same factor. That is, if I increase the free stream velocity by a factor of 2, velocity at every point increases by a factor of 2. Okay, or the velocity at every point increases by a factor of 2. Because of that, the pattern of the velocity does not change as the Reynolds number changes. And what that means is that all of the information regarding convection is contained in the Peclet number alone. Okay. All of the information regarding convection is contained in the Peclet number alone. The Reynolds number contains information about the flow pattern, but at low Reynolds number the flow pattern does not change. Okay. So, all of the information regarding convection is contained in the Peclet number alone, and in this case the Nusselt number and the Sherwood number are functions of the Peclet number alone. Okay. In this case, the Nusselt and Sherwood numbers are functions of the Peclet number alone. Okay. This is specific to low Reynolds number and high Peclet number transport. Okay. And of course, if you go to high Reynolds number and high Peclet number, the Nusselt number and the Sherwood number are functions of both the Reynolds number and the Peclet number. Okay. So, those are the broad categories of transport processes, the dependence of Nusselt number and Sherwood number on the dimensionless groups. We will continue in the next lecture by looking at specific cases, flow through a pipe, flow past a particle, and so on. Okay. So, I will continue this in the next lecture. I will see you then.